As engineers, we make many versions and iterations of our products. It helps us optimize our products and find the best dimensions and forces for our designs. But making physical iterations of our designs would be very expensive and very time-consuming. Think about if Boeing made a new airplane every time they wanted to see a change in a single dimension. That would cost at least $90 million with every iteration, and a lot of time. Or what if NASA missed an optimal or critical design choice because they didn't have time or resources to calculate iteration after iteration? This is why we have engineering models, so that we can iterate designs and accurately predict how a product will react in its environment. We can estimate when and how it will fail quickly and at a low cost. It's an easily adaptable solution to the many engineering problems we face in the real world.
We used these engineering models in our Scissor Jack project in order to better understand the problem. The first problem was understanding how the different geometries affect the failure modes that we selected. This MATLAB model allows us to iteratively analyze the structure, looping 50,000 different random combinations of possible dimensions in each run. To ensure that each geometric combination was viable, we manually selected a range for each dimension. These ranges were chosen such that no one dimension interferes with the possible dimension of another, meaning any combination can be built without geometric complications. For example, we made sure that the largest pin diameter possible fits within the smallest hole diameter. Upon running, the code generates 50,000 random combinations of dimensions, and then analyzes the combined weight of all parts. Since one of our design requirements is weight, we then filter all resultant weights of all combinations and only consider those that meet our requirement. These new dimensions are now considered viable. Then, using fatigue analysis, we calculate the fatigue strength of our chosen material. This is done so that we meet our second design requirement, which specifies that our design must withstand 10,000 cycles. Now, with the new viable dimensions, we run structural analysis to calculate the failure loads for all failure modes. These loads are then compared to one another, and the smallest load in each dimension combination is stored in a max load string. Finally, the largest load in the max load string is pulled, resulting in the max critical load for the 50,000 iterations. Along with the value of this load, the failure mode of this load is also displayed, along with all dimensions that produce this value. Running this model over and over produces a new combination of dimensions and a new max load for each run, allowing us to truly optimize the design of our model.
Hand calculations are a necessary part of validating any model, as it ensures that the model is working based on both intuition and calculated equations. For our Scissor Jack model, we made preliminary calculations with arbitrary ballpark dimensions to calculate the maximum force and how the Scissor Jack failed. We then compared these values with the preliminary version of our code and ensured we got the same values as our hand calculations. This is extremely helpful as we found small errors in our code, such as a missing negative sign or the wrong dimension used. We did hand calculations for 2 different materials to make sure both matched the code, and even made sure the code matched our preliminary hand calculations we did in a homework assignment for the Scissor Jack.
Even though hand calcs are great, sometimes we need to use finite element analysis. Finite element analysis is great for the components that aren't easy to do hand calcs for. For example, the pin, which is what we did our analysis on. It has a hole through it, so it's hard to analyze with hand calcs. Finite element analysis is always great for things that are modeled correctly. You have to make the model correctly, otherwise it doesn't work. For ours, we were just looking at the equivalent stress and the shear stress and seeing if anything was bad or too high of a stress that looked like it would fail.